So this is a famous example that always needs to be studied in deep, which is related to gas blow-by case. Suppose that we have this vertical vessel operating at 30 bar gauge and its design pressure is 35 bar gauge. The accumulated liquid is transferred to another horizontal vessel operating at nearly atmospheric pressure, and it has a design pressure of 3 bar gauge. The pressure is reduced through the control valve that changes its opening depending on the signal it receives from the level controller based on the level in the vessel. So let's imagine that the level transmitter is giving a false reading or that the control valve is stuck in an open position. In this case, the liquid level is expected to keep on falling until the vessel is emptied from liquid. Now, the gas starts to get into the low pressure system and the pressure shall keep on rising until failure occurs in the system. So we want to prevent this from happening. Of course, we can increase the design pressure of the whole system to 35 bar gauge, and in this case, the system would be inherently safe. However, this shall cost too much, as this is not just related to the vessel, but also to piping, valves, fittings, and instruments for the whole system. We shall need to consider a flange rating of 300 pounds at least for the whole system instead of 150 pounds. So here we would need to protect the low pressure system externally. First, we want to stop the flow to the low pressure vessel in case there is no enough liquid to be transferred. So we shall add a level transmitter to measure the low liquid level in the high pressure vessel. And if this level was too low, the level transmitter shall send a signal to ESD system, which shall send a signal to an on-off valve to stop the flow. This is a safety function, and that's why it's totally distinct from the level control. We are using a different device to measure the level. Still, there is a probability for the safety system to fail on demand. That's why it's common in such systems to consider cell rating of 3 to reduce the probability of failure on demand. In many cases, this is not applicable, so we shall need to mitigate the risk. That's why we also added a safety valve to open in case the pressure in the horizontal vessel opened at 3 bar gauge, which is the design pressure of the vessel if you recall. Here, there is something that is very important to note. There may be already a PSV on V2, so would we need to add another PSV? As we explained before, this depends on the case on which the PSV is sized. Most vessels have a PSV that is sized for fire case. However, if we introduce the gas blow-by case, this may need larger PSV. So we are considering here the gas blow-by case. We should check if the current PSV can handle the relief load in case of gas blow-by case, or we shall need a greater PSV. So these examples show the common approaches that are followed to protect our plant from major deviations. These should always be well studied in order to ensure that the plant is well protected and reduce the accidents to a minimum.